Okay, YouTube, in my last two videos in which we've solved polynomial inequalities, we've looked at examples that include quadratic functions or parabolas and looked where their y-values are greater than or less than 0, which is kind of a pretty basic thing to do. But in this video, we're going to look at a third degree polynomial and consider its test intervals here. And so let's start with this. Solve and graph the solution set on a real number line, our instructions here. And of course, we want to start by getting a 0 on one side. I'm going to clear this right side here. So I'm going to rewrite my initial inequality here as x cubed plus 3x squared minus x minus 3, and of course we would have less than or equal to 0. So here's our initial inequality. The first thing we want to do is get our critical values. So I don't need to write critical values. I did leave a space over here. But I suppose I do want to set this equal to 0, which is the first thing we should always do here. If we're going to find the critical values, what we know is these occur at the zeros of the function. And so we'll go ahead and I notice here a four-termed thing we can factor by grouping. I'll put a plus here. And I notice that an x squared comes out of the first two terms here. We get left with x plus 3. And then here we can take out a negative 1. And so we get left with x plus 3 over here as well. They both of these terms here that we're adding together have an x plus 3 in common. So if we carry that x plus 3 out front, and we notice we get left with an x squared minus 1, which also factors, essentially the completely factored form of this expression here, whoops, be x minus 1, its conjugate, would be this. And so if we carry all of these factors off and we set them equal to 0, what we determine is that our critical values will be at negative 3, negative 1, and positive 1. So we're going to write our critical values up here. We say negative 3 and also at plus or minus 1. So these being our critical values here, what this is going to allow us to do is set up our number line and put our critical values on it and set up our test intervals. So let's see, 0 will go out to 5 on the right, 5 on the left, and make sure we label these. Okay, so we're going to put x's for our critical values here. I know I have one at negative 3, negative 1, and positive 1. So these values right here, our function can go from having positive to negative y values or vice versa, possibly. Okay, so our test intervals, these would be 4 intervals this time, or we would have 4 intervals because we have 3 critical values, but we say from way out on the left up to our first critical value, which is negative 3. From that critical value to the next critical value, which is negative 1, and from negative 1 to our next critical value, which is 1, and then finally that last critical value out to the right. What we're going to look at here is testing x values in each of these intervals. So let's pick them out. I would say I would test x equals negative 4. I would certainly test x equals negative 2 would be an easy one. Always x equals 0 if you can, and then x equals 2 here. We'll test each of these values into our function. And so one thing I want to kind of point out here is this. I did indeed put this into my graphing calculator, and I can already, if I go take a look at the graph here, we can see this third degree polynomial that changes from being negative to positive and then positive to being negative and negative to positive here on the number line. So we can already say that because the y values we're after here are all, well, the x values we're after here are where all of our y values are less than or equal to 0. We're looking for all of the x values for which our graph has y values below the x-axis. So we know it's going to be to the left of this negative 2 here, and also between negative 1 and positive 1 our graph has below the x-axis y values. So that's where we're going to get our solutions here. I'm going to cheat a little bit on this video, and what I'm going to do is I'm going to pop over to my table. So what we're going to find out here is this. If we were to plug in these particular x values into our function, what would our y values be? I'll make a little chart here. We say x and f of x. So we were going to plug in negative 4, negative 2, 0, and 2. And using our calculator here, we can say, scrolling up here, negative 4 is at negative 15. Negative 2 is at 3. So we have negative 15, we have 3. At 0, well, I can just look up here and say that I would get my constant term, so we would get negative 3. So we get negative 3. And then at 2, if we look back at the table here, at 2 we're at a height of 15. And so essentially what I want you to see is that in each of these cases what we were asking is where f of x is less than or equal to 0. And so what I want to know is, did we get true or false values here? So negative 15 is less than or equal to 0. It's true. Whereas if we were to say now 3 is less than or equal to 0, that's certainly a false statement. Also, negative 3 is less than or equal to 0 is true. And we say 15 less than or equal to 0, that is a false statement. In terms of solution intervals then, what we would want are the intervals for which our initial inequality is actually true. So because negative 4 was on this interval here, we'll shade all of these points to the left here. And also because it was true when x equaled 0, we know that all of the x values in between these two critical values give us true y values here. And lastly, because this is a less than or equal to, what we're going to do is we're going to put inclusion brackets here. We're going to include those critical values. So our solution intervals, if we're going to write these, are from negative infinity to -3 on our graph here, including 3, in union with, now including -1 up to and including +1. Cheers.